Welcome back from break. Now we are going to finish up the topics from chapter 3. Now we are moving on to section 3.6, which specifically talks about specific heat. Specific heat is defined as the amount of heat that raises the temperature of exactly 1 gram of a substance by exactly 1 degree Celsius. It has units of joules per gram per Celsius, or it can have units of calories per grams per Celsius. Understand that different units of mass or temperature can also be utilized, but these are among the ones that are most common. Now, when it comes to specific heat, I want to point out that it is particularly important to understand what a specific heat is. In Chemistry 104, I don't go over the specific calculations for specific heat. I utilize the concept of specific heat more as an application, okay? So let's view specific heat as an application, okay? So overall, to break it down into regular English, what specific heat is going to tell us is that if I have different substances, and I apply heat to them, one substance will raise its temperature faster than the other one, depending on the value of specific heat. That's overall what we're looking at. So in terms of its applications, let's see, for example, the image that we have here. We have a pot that has a substance, okay, that is receiving heat. And it's in liquid form. Remember, earlier today, we learned how heat is going to transfer from things that are hot to things that are cooler. Let's say that we put in different spoons that is made of different materials. You can see that the spoon that is towards the right is made out of wood, but the spoon that is in the left is made out of metal. And at home, you guys, maybe you had to do this. You know, maybe you were making sopa, you were making some soup, you were making caldo, your mom was making caldo. And I don't know who this happened to, but growing up in Puerto Rico with my mother and my grandma, you left that spoon inside of the boiling pot, all of a sudden, maybe you will get yelled at. Now, there was a reasoning why different sorry, you guys, for anybody that's getting hungry again, I'm sorry. But we are looking at, like, you know, how this applies to things that we do at home. So at home, at least I grew up with females that were, you know, doing most of the cooking, and they always had a system. They had pots and pans for certain uses. They even had certain spoons that you can utilize depending on what you're cooking. Now, if we look overall here, let's look at the specific heat of the materials of the spoons, okay? So here, and I'm just going to use my highlighter tool, the wood spoon, okay, wood actually has a specific heat that it is 0.42. Okay. Now, let's assume that the metal one, the metal spoon, is made out of aluminum. Let's just assume that. Okay. While the aluminum, just to select something from here, will have a particular specific heat. So if I write down these values, I see 0.42. I'm comparing it with something that has a specific heat of 0.21. Okay. Again, here we're doing comparisons. The application here is not that, oh, if something has a specific heat of 0.42, this is the result. No, I'm comparing the two substances that I have in, my boiling broth, sopa, caldo, whatever you want to call it. So you can see here in the notes, as I zoom in, and maybe you have experienced this at some point, that if you are leaving in there a wooden spoon, even though the liquid is hot, the wooden spoon, when you touch it, is going to be feeling warm. But again, if in the same container, you have a metal spoon, and let's assume that it is aluminum, it will feel too hot. So let's now rationalize it based on specific heat. My metal specific heat is lower than my wood spoon, because I can see the values. The specific heat is 0.21 versus 0.42. So if I rationalize it, I'm applying the same heat because they are in the same container and my spoons have the same mass. So the only thing difference is the specific heat. What this is illustrating is that substances that have a lower specific heat will get hot faster. Okay, I'm just going to write it here in the notes. So when comparing two substances, the one with the lowest value for specific heat will heat up faster. So that's what we're trying to illustrate here, that I have two substances, same grams, I'm applying the same heat, but to touch, one is going to be warmer than the other one or hotter than the other one. Which one do I know that is going to, absorb that heat faster? The one that has a lowest specific heat, okay? Now, let's do another application of this. We have two more examples for you guys. This application, again, cooking is my hobby other than chemistry, okay? Now, who is with me? Who likes cooking shows? Put a 1 in the chat if you like cooking shows. I love Iron Chef, Master Chef. It doesn't matter if it's adults, if it's kids, holiday baking challenge. Baking is not part of my ministry. I am not a baker. I can cook really well, anything. Put me a recipe and I can cook, but baking is not part of my ministry. I don't know. Yes, I agree. I also have Discovery Plus because of the cooking shows. See, there's people that get me. I do the same thing. Oh, I love to see baking shows because I know I cannot do that. Like, I really have to focus myself into baking. It's even though I'm a chemist, I'm like, it's baking is so exact that I'm like, oh, there you go. There's bakers out there. Great. Hats off to you. That is not part of my ministry. Baking is not. So let's get back to chemistry. So you guys may have seen, or even at home, similar to what I was explaining, growing up with my mom and my grandma, they have pots for boiling water, pots for making the rice, pots for, making caldo or whatever. They have different pots for everything. Seriously. Now, when I was a kid, I was like, this is too much. But now as an adult, I do the same thing because now I understand the logic behind it, okay? Let's utilize the concept of specific heat to actually rationalize why may you want to use different pots for different purposes in the kitchen, okay? So, for example, let's assume that these three pots have the same mass, okay? We can see that we have aluminum, copper, and iron in it. Let's say that you are, for example, another one of my favorites, chopped. I love chopped because these people are generating meals in like 15 minutes, 30 minutes. Seriously, I'm like impressed. So let's say that you are in that show. I don't know if you guys have actually noticed, like they actually take pots and then sometimes they forget about it and they're like, why is this water not boiling? Let's rationalize why. So let's say that you put the same amount of water to each one of these pots. Again, you have a copper one, you have a cast iron one, you have an aluminum one. So if each of them, let's say that they have 10 grams of water. You put 10 grams of water. Oh, let's do 100. That's going to be better. Let's say that we put 100 grams of water on each of them. And then you apply the same amount of heat on it. Great job, Jessica. Yes, copper will heat up faster. Because when we look at the specific heat, in this case, we have different units. It's joules per kilogram per Kelvin. But when we look at this, we see that copper has the lowest specific heat. So that's why copper overall, if you're trying to heat up water faster, this will heat up the water the fastest. And again, it's from the logic of, since you have a low specific heat, the amount of heat that needs to be applied to this substance, okay, it's going to allow it to reach temperatures higher, faster, because the specific heat is lower. Last semester, I had a student that utilized a really awesome analogy to think about specific heat capacity in substances. The student brought up how you can visualize specific heat as a different levels, right? So the lowest level will be copper, and then aluminum will be the last one. Iron will be in the middle. So then if you apply heat, okay, the one that is the lowest is the first one that it gets reached. So if you think about it in terms of what we're doing, which is applying heat, the first one that you reach when you align them from lower specific heat to higher specific heat is the one that heats up the fastest. Now, you guys, specific heat has application in a lot of things. In construction, depending on the materials that you utilize for building a house, you can consider specific heat in order to utilize certain materials in order to allow the house to actually not get heat up faster. So if you have ever visited Arizona or other sites in which houses are made out of adobe or mud, understand that there is a reasoning what the house is made out of that. And again, it comes from the idea of specific heat. The specific heat for those materials is higher, so it's not going to heat up faster, okay, compared to other substances, okay? So this has applications, as you can see, in the kitchen, in construction. And another thing that we live in Southern California, so we enjoy going to the beach on a hot summer day, which is the example that it is in the in-class worksheet. When you go to the beach and it's hot outside, let's say that all of a sudden we're in the 90s and you go to the beach, what is hotter, the sand or the water? The sand, right? So which one do you think has a lower specific heat, the sand or the water? Excellent, the sand. So remember, when the sun is hitting the sand versus the water with all of that light energy that has been transferred, because the sand has a lower specific heat, it will heat up faster compared to the ocean water. So as you can see, specific heat is all around us and it has multiple applications. Any questions when it comes to specific heat? Yes, that's correct. It takes more energy to heat up the water. Yes, when it comes to the size of the object, it matters, because remember that whenever we are doing these comparisons, that's why I kept on mentioning to you guys, let's assume that what we're comparing has different, whatever we're comparing has the same mass. So whenever we're doing comparisons for specific heat, we are comparing in terms of mass the same thing, because if we look at the units for it, we can see that specific heat has joules, which is the energy that is in there, grams, and then temperature. So whenever we are doing these comparisons of the different spoons, the different pots, we are assuming each of them have the same mass, and then that we are applying the same heat. And then basically what we're looking at is, what is the temperature that is added in? How is that going to make the substance heat up faster? So if you have objects that have different mass, then understand that that can affect overall how is it being heated. That you have to do in the laboratory in order to know, because there's also thresholds, right? On how big is your copper pot need to be compared to the aluminum. Any other questions when it comes to specific heat? That's a great question. There you go. That's a question that maybe I should bring it to class in the fall when I'm teaching lab. Excellent. Since there are no other questions, let me make sure that I didn't miss any other ones. No. So since there are no other questions, now we are going to move on to the concepts of chapter 4. So far, you guys, we have learned how to take measurements. We have learned how to do calculations. We have learned the definition of matter. We know how to classify it. We know the properties. We know the changes that matter can undergo. Now we are going to look at matter, but in terms of the atomic level. So in chapter 4, we are going to specifically look into atoms and the elements that make up that matter. So in the previous chapter, we already learned that elements are pure substances. And the elements that are in the world, okay, understand that when they are by themselves, or sometimes they are coming together to make compounds, that's what things are built from. Now, another thing about elements is that they cannot be broken into simpler substances, okay? So the atomic level, the element, okay, may have subatomic particles, but understand that the element is one of the simpler atomic levels that we have in terms of pure substance. Now, here I have an example of a periodic table that actually illustrates with images how these elements look like. So you guys can see overall, and I'm just going to zoom in so we can look at it, that starting in the corner, we have hydrogen, and then we have it is very varied what we have in terms of elements. And notice that we have samples of many of them, okay? Some are shiny, some are not shiny, some are gases, some are liquids. And when we get into past element, I will say like 95, we start seeing pictures of people. Sometimes we see shields. And that is because when it comes to elements, we need to understand that elements are discovered. There are a number of them that are obtained from nature, but there are other ones that have been created in the laboratory. And you can see here that we specifically, the ones that have images of people, those are the ones that have been created in the laboratory, and they were radioactive and short-lived, so we don't have samples of them in nature. I don't even think that we have compounds made with them, to be honest with you guys. So understand that not all elements are actually found in nature. So taking that into consideration, how do elements get their name? Well, it comes from people naming them whatever they want, okay? It can be planets, it could be mythological figures, it could be minerals, colors, geographic locations. We can have famous people. In table 4.1, you have the example of some elements, what's their symbol, and what is the source of their names. Just to illustrate how cool this is, we have here one of the two examples of elements that have been named after the state of California. So you can see here, California, which the symbol is CF, and it comes, is named after the state of California. If we look at the periodic table, the other element that is named after the state or after something in the state of California is right before California. Is this, wait, give me one moment. Berkelium. So berkelium, element 97, is the other one that is named after a place in California. That's named after the University of California at Berkeley, okay? Did I spell Berkeley wrong? I'll fix it before I post the notes. But those are the two. So 97 and 98 are named after places in California. One after the state and the other one about a university. Now, what do you guys need to know when it comes to names and the elements? You guys need to know this list. I cannot stress enough how important it is that you guys know the symbol, the names for elements. In addition to that, I want to point out, it is important that you guys also know how to spell them correctly. Yes, my friends, spelling is necessary. You need to know how to spell them correctly. Understand that chemistry is just, like a language. I speak English, Spanish, some French, and chemistry. It is important that you guys memorize this list. So from here to the exam, understand it is important that you know how to write the symbol, how to write it correctly, and how to spell the name of elements, because starting next week, we are going to go over chapter 6, in which we are going to be going over naming compounds. So work on this list, please. Now, when it comes to the symbols, you can see that the symbols of the elements can be one letter, as you guys can see here with hydrogen, or they can be two letters, like you can see here in sodium, okay? If your element has only one letter, understand that it is a capital letter. If your symbol has two letters, the first one is capitalized, the second one is not capitalized. When it comes to writing the names of the elements, understand that in the instructions, I tend to tell you guys, hey, do not capitalize the name of the element. So please get used to the habit of not capitalizing the name of the element also. This list can be found in the reference list for exams, which is a Word document that I created. It's about 4 to 5 pages, which is the information that I typically give in exams when students are taking the class face-to-face. But for you guys, because you're online, I provide the list completely. This is the first table on page 1. That's where you can find this list. So again, make sure that you know name, symbol, and correct spelling for the elements that are here. So there are 118 elements. You guys don't need to know the 118, but these in this table is what is required at least for this class. So let's now dive in and talk about the periodic table. As I mentioned a few moments ago, to date, there has been discovered 118 elements. And you can see here that it has been organized in what we call the periodic table. So the periodic table has an organization. This, understand that it is organized based into groups that have similar properties. And understand that currently, the organization of the periodic table is based on increasing atomic number. You guys will be exploring the periodic table in lab 3 next week. Now, who started thinking about organizing the periodic table? Well, that is thanks to Dmitry Mendeleev, which is the image of the person that you see on the right. He was a Russian chemist that developed the first classification of elements. When he started organizing it, he did it differently. He arranged them in increasing atomic weight. Understand that that is not the way that it is organized now. We organize it now by atomic number. And in a few moments, we are going to talk about atomic number. Now, as I mentioned, when it comes to the periodic table, it is organized. It is called the periodic table because of its organization. Overall, when we look at the periodic table, it is organized by groups. And the groups here are the arrows that are pointing down. Understand that this whole area right here is also called a group. Okay? So the groups are going to be the vertical columns that we have. So that's why the arrows pointing down. Now, the periodic table, it is also organized into periods. And understand that the periods are going to be the horizontal rows. So the periods are going to be the rows that we find in the periodic table. And when it comes to the periods, understand that we're going to have 1, 2, 3, 4, 5, 6, 7. There are many groups, but there's only 7 periods, okay? So When it comes to the periodic table, as I mentioned to you guys, I provided to you guys a periodic table, which is in the resources for exams. It is a blank periodic table. That periodic table doesn't have the names of the elements. The one that I put in the slide does. So you can see. This one does. The one that I put over there doesn't. Understand that whenever I'm grading, I utilize the one that doesn't have any names. Okay, so the periodic table that is provided to you in Canvas is the one that I utilize for all the information that I give you guys. So when it looks to the periodic table, we can see the group numbers, and they're given by the letters 1A, you can see the Roman numeral, or the regular digits 2A, and then we have 3B, 4B. Those are the different groups. I'm just showing you guys the groups. Let me label them. So the groups in the periodic table, we can see them here. These are the notations given. And then when it comes to the periods, as I mentioned, there's 7 periods in the periodic table. Okay. Now, when it comes to the group number, there's some information that we need to know. Group numbers are written on top of the vertical column. Typically, when we're doing these problems, I utilize the designation that is a number and a letter. Okay, so you can see that when it comes to the representative elements, that's going to be groups 1A, 2A, all the way to 8A. You can see them here. 1A, 2A, we skip, wait, sorry, no, I skipped too fast. 3A, 4A, 5A, 6A, 7A, and 8A. Okay, those are your representative elements. Then we have the transition elements, which is group 3B all the way to 12B. So if we look at this periodic table, you see your transition elements here from element 21 all the way when we look across to element 30. When we go down from 30 to 112, understand that the elements from 57 to 71 and 89 to 83, they are not transition metals. They are actually called lanthanides and actinides. And they are excised from the periodic table because basically these rows have similar properties. Those are the only rows that have similar properties, and they are taken out of the periodic table. But all the transition metals, okay, are there in those columns. Understand that 57 through 71 and 89 to 103 are not part of group B. They are completely separate elements. Now, there is an alternative system that you can also see in the periodic table that I use in the slide, where assigns the groups number 1 through 18. I don't use that alternative system. So when we practice now, understand that I'm going to use as a reference either the period number by itself, or when I want a group number, is going to be a number and a letter. Okay. Now, I understand that both systems are utilized right now, but understand that in the class, I have a preference of doing the group numbers in terms of number and letter A or number and letter B. Now, groups also have a particular name. Not all groups have a name, okay? Only some of them. So there are 5 different group names that you guys need to know. Group 1A, okay, are going to be the alkali metals. Now, understand that when it comes to that, is the elements in group 1A except hydrogen. Hydrogen is not a metal, as we're going to see in a few moments. In group 2A, those elements are known as alkaline earth metals. The elements here, which are in group B, are your transition elements or transition metals. Understand that 3A, 4A, 5A, 6A, they don't have a common name. In addition to 1A, 2A, group B, column 7A, all of the elements there are known as the halogens, and the elements in column 8A are known as the noble gases, okay? So at this time, I want us to utilize the information that we just learned in terms of the periodic table and answer the following questions, okay? Understand that in part A of the in-class worksheet, you need to identify the group or period number described by each of the following statements, okay? Then in letter B, we're going to give the name and the symbol that is described by each of the following. So let's get started with, this is why it's important that you guys know element and symbol, because I don't want you guys on exam 1 to be scrambling along looking at, oh, what that name, and then what is that symbol, and where is it in the periodic table. Familiarize yourself with them, okay? So as you can see here, let's go with number 1. I'll do number 1 and number 2 with you guys. It says contains the elements indium, tin, and antimony. So when I look at, let me just copy it and bring it here for our use. When we look at indium, tin, and antimony, let me use my highlighter tool. Indium, tin, and antimony are here, okay? All of them are in the same group or in the same period. Let's establish that. Great job, you guys. Exactly, in the same period. What period is that? Excellent, in period 5. So period 5 contains all of them, okay? So remember, these statements, it's for either a group or a period, and all of the information needs to be contained there. Number 2, begins with fluorine. So if we look at the periodic table, let me use my highlighter tool. Fluorine lives right here. Excellent, you guys are getting the hang of it. Great job. Let's actually move on to part B. So I want to at least show you guys 2 examples, and then you guys do the other 3 on your own. So if we look at part B, see how it says group 5A, period 3. So this is kind of like a little bit of a scavenger hunt. So when we look at the periodic table, again, it says group 5A, period 3. So if we look at 5A and period 3, let me use my highlighter tool. We are at period 3. We land on 5A. So we're talking about this element. Great job. This is phosphorus. Understand that the way that I spell phosphorus is based on the US English language. Be careful with the naming. P-H-O-S, P-H-O-R-O-U-S. So if phosphorus ends in O-U-S, that's British. And if you put the British spelling of the element, you will get it incorrectly, okay? So be conscious about that. That some are British spelling, okay? Next one, halogen in period 5. So which group number is where the halogens live? Ooh, some people got it already. Great job. So when it comes to the halogens that live in 7A in period 5, that is iodine. Oh, you guys are going to do so well in this exam. So iodine, and the symbol for iodine is capital I. So at this time, I'm going to give you guys, we should go through these fairly quickly. So I'm going to give you guys 2 minutes to finish the 3 to 5 on part A and part B. I'll give you guys 2 minutes and we will go over it in class. Let's get started. So what is where we find the noble gases? Is it a group or a period? Excellent. Thank you for the answers in the chat. It's going to be a group. And this is group 8A. Now, magnesium, calcium, and strontium. Where can we find those? Magnesium, calcium, and strontium. Great job in group 2A. For those students that need to see it in the periodic table. Magnesium, calcium, strontium, element 12, 20, and 38. That's where we find them. Lastly, it contains cobalt, nickel, and copper. Cobalt, nickel, and copper. Great job. We look at the periodic table. Cobalt is 27, nickel is 28, copper is 29, and they all live in period 4. Excellent job, you guys. Let's move on to finding the name and the symbol for those elements. We're still in period 4. Who lives in 7B? 7B. And it's period 4. Great job, manganese. Then we have the alkaline earth metal that is in period 6. So alkaline earth metal in period 6. So the alkaline earth metals is group 2A. Great job. Barium. And barium only has one R. Lastly, we need to find somebody in group 3A from period 3. Great job, you guys. Exactly. Aluminum. Remember that the spell of aluminum is not aluminium. It doesn't have an I between the N and the U. It's aluminum. Okay, so be conscious about the spelling, you guys, when it comes to this. Any questions on the little exercise of scavenger hunt utilizing the periodic table? Excellent. So the other classification out of the periodic table that you guys need to be familiar with when it comes to these concepts is going to be, where can I find my elements that are metals, non-metals, and metalloids? It is important that you know which elements are metals, which elements are non-metals, which elements are metalloids, okay? Now, when it comes to this, you guys, I always suggest to students, memorize the metalloids. Seriously, it's the best thing that you could do. Memorize the metalloids, because to the right of the metalloids, everything is a non-metal, okay? And remember that hydrogen, even though it's sitting in 1A, it is a non-metal. That's the only one that is the non-metal that is not with its crew. And then to the left of the metalloids, everything is a metal. Done. Now you know the classification of the periodic table. Okay? So what makes elements be categorized as metals, non-metals, or metalloids? Well, it is all based on their descriptions. Metals are going to be elements that are shiny, that are ductile, meaning that they can be drawn into wires. Metals are also good conductors of heat and electricity. Among the characteristics of nonmetals, it includes that they are dull, meaning that they're not shiny, they're brittle, okay, and they're poor conductors, but they are good insulators. On the other hand, when it comes to metalloids, understand that metalloids are a class on their own, okay? They don't look more like a metal than a non-metal. They have some of each of them, so they are their own group. When it comes to metalloids, understand that they are going to be better conductors than the non-metal, but they're not going to be as good as the metals. That's why they are sometimes used as semiconductors and insulators, okay? So for example, in the semiconductor business, and up north, we have specifically Silicon Valley, which is where there's a lot of technology and there's a lot of computer-based companies like Apple, Google, so on and so forth, okay? In computers, some of the components of the computer actually have elements in it. And as you can see, silicon, which is actually a metalloid, is one of those elements that is utilized in computer parts. And that's where the whole idea of Silicon Valley actually comes from, okay? But again, when it comes to the categories in terms of knowing which elements are metals, non-metals, and metalloids, memorize the metalloids, because other than that, then you have to say, oh wait, if the element is to the right of the metalloids, that's a non-metal. I have to remember hydrogen is a metalloid. It's not an alkali metal. And then to the left of the metalloids, everything is a metal, okay? Any questions in terms of the classification of elements based on being a metal, non-metal, and metalloids? Great. Now we are going to move on to section 4.3, where now we are going to look at a little bit of a history lesson. So we know so far that the elements in the periodic table are made out of atoms. And as you can see, the atom is the smallest particle found in an element. And this particle is going to retain the characteristics of that element. So for example, you can see in the little image that we have in the top right corner how we have a sheet of aluminum foil. So aluminum foil, aluminum is an element, and understand that that aluminum foil, when you look at it at the atomic level, it is made out of aluminum atoms. So each one of those silver balls that we see here, they are going to represent an atom of aluminum. Now, what I'm trying to show you guys here is that this took many years to understand elements at the atomic level, and it all started with Greek philosophers. So in this timeline that I have here, you guys can see that this goes all the way back to around 400 to 300 BC. Okay, so it's been a long time and a lot of experimentation that had to happen in order for us to understand the elements at the atomic level. So where all of it started, as I zoom in my timeline, is with Democritus, okay? So I always try to talk about this in terms of like soap operas. You know, growing up in a Latin household, you know that novelas are our jam, especially after school. Put a 1 in the chat if you have seen novelas in your life or you've been around people that enjoy novelas. And if you're like me, growing up with my grandmother, she will be yelling at the TV like, "Mija, but why are you with that guy?" And I'm like, "Grandma, you know that she is going to be with that guy." And soon enough, you're going to find out that they're siblings, but they're not siblings because the mom, you know, cheated on the husband. It's just hilarious. Novelas are just something else. Okay. Now, let's just look at this history, but just with a little bit of more enthusiasm, because again, history at times, if we don't spice it up, then it may be like very boring. So let's get started with atomic level and understanding how Democritus made an important contribution to the way that we understand atoms. So around that time, that of around 400 to 300 BC, there were many Greek philosophers trying to understand the world around them. They were trying to come up with theories to explain the substances that were around them. Now, during that time of Democritus, Aristotle was the more popular Greek philosopher. Now, everybody was like, you know what? Aristotle, he is the one that knows everything. He can just tell us what are these substances made out of. And when it comes to understanding the materials around them, Aristotle said that all the stuff around them was made out of the 4 forces of nature coming together and creating everything. So for those of you that understand this whole idea of you have taken Greek, philosophy or any type of philosophy at some point, what are the 4 forces of nature? What are the 4 forces of nature that Aristotle was talking about? Exactly, wind, fire, earth, water. So according to Aristotle, those things came together and make the substances around them and the world around them. And then what's the underdog? Okay, so just imagine that Democritus is like Mariela del Barrio, for those of you that understand the novela references. So Democritus at that time was like, you know what? I don't think that the four forces of nature are the one that actually make all the substances around us. I think that the substances around us are made out of small particles that I'm going to call atomos. And these are tiny, hard, particles that we cannot cut them. And depending on the shape of them, then they're going to have different properties. So that's why on the top of Democritus, you see that in his idea, these atoms that were making these substances, if they have a sharp taste, is because maybe their shape is sharp. Maybe if they're smooth, then they're round, okay? So he was just visualizing these atomos, okay, in terms of shape. But he actually said, I don't think that the forces of nature are the one that making, I think that is more at a level that we don't understand, but I'm going to talk about it in terms of shape, okay? And because Democritus was the underdog, nobody believed him. Everybody was like, what? You don't even know what you're talking about, dude. Now, it took you guys until 1803 to prove that my boy Democritus was right. John Dalton actually illustrated experimentally that the material around us is actually made out of atoms. So the word atoms actually comes from the Greek word atomos that Democritus used. And John Dalton described how substances are made out of these atoms that are solid, indivisible, okay? And he describes them in terms of a sphere. So he just changed the way that we think about it in terms of shape. He said, like, they're actually round just because of their composition. But the most important thing is that John Dalton said, hey, this is the first atomic theory. I'm showing it experimentally, and these particles could not be destroyed or reconstructed. Then, as you can see, 90 years later, a little bit more than 90 years later, people started saying, okay, John Dalton, great theory. Let's actually think about how these atoms actually are. Like, is there more to it? Or is the atom the smallest thing and there's nothing inside of them? So J.J. Thomson actually started doing experimentation to see if the atoms have other parts to it or it was just this solid indivisible sphere. So J.J. Thomson did what is called the Cathode Ray Experiment. And in this cathode ray, just imagine that he had the ability in the laboratory to create a beam, okay, of the sources of the atoms. And then he started experimenting by putting his hand over it, putting objects of it. And when he actually put a magnet on it, he actually discovered, okay, that the atoms that John Dalton talked about had different components to it. J.J. Thomson was the one, give me one moment, that discovered the existence of electrons. So he was the first person that discovered that they were subatomic particles. And because he saw that they were attracted to the positive end of a magnet, he said, like, oh, they must be negative charge. Let me call them electrons. Okay. Now, at the time of J.J. Thomson's discovery, he said, well, if there are negative particles in these atoms, which I'm going to call electrons, then we know that electrons cannot be free floating. They need to be contained in an area that have an opposite charge. And this area, I'm going to say that it is just going to be plus charges in that is all around them. So when he proposed the structure of the atom, then you can see over there that is still a sphere in which the electrons are these circles right here. And so far he said, do you know what? Those electrons are just going to be just swimming in a sea of positive charge. That's why the blue area is positively charged. Now, his model was called the Plum pudding model, just because that is a dish that is found in his country. You know, think about it as a blueberry muffin, in which the dough of the blueberry muffin is that sea of positive charge that he's proposing, and the blueberries themselves is going to be the electrons, if we want to rationalize it with something that maybe we commonly have seen. So understand that around a little bit more than 10 years later, people were still thinking, you know, chemists, physicists, thinking of like, okay, these are great discoveries. Like these atoms are actually quite interesting. So around 1909, Rutherford actually did an experiment to prove that J.J. Thomson was correct in this whole idea of electrons, okay? And he did what is called the gold foil experiment. And in the gold foil experiment, what he did specifically is that he actually had gold foil, and we know that gold is an element. And then what happens is that this gold foil was then, you know, in the experimentation, there was a beam that was exposing the atoms of that gold. And what he was trying to say is that, okay, if indeed atoms have this sea of positive charge, then when I do my gold foil experiments and I put a beam of, I'm just going to call it of light, it is actually of different particles, but I don't want to go into these specifics. When he actually looked at the beam that he put through the gold foil, he's like, if this is an overall sea of positive charge, then at the other end of it, I should see specifically the beam going through. And he did see that. The thing is that in the gold foil experiment, he also see that the beam that he put through the gold foil scattered. And then at that point, he was like, wait, if it's scattering, then the positive charge is not all over. The positive charge is actually centralized. So with Rutherford's gold foil experiment, then at that time, people started thinking, oh, wait, no, the positive charge, it is in the middle. So Rutherford, with his contribution, he said, you know what? The positive charge is in the nucleus. And then other scientists actually found that that positive charge that is in the nucleus is because there are other particles that are living there. So understand that this is from other scientists discovered that that positive charge is because we have protons and we have neutrons in the nucleus. But the most important thing is that Rutherford actually showed that specifically there was positive charges concentrated in the nucleus, okay? And then the negative charges were all around those, okay? Now, at that time, there was a lot of investigations that led to the consequential understanding of, we know that the protons are in the nucleus of the atom. We know that there's neutrons in the middle of the atom. Now we are going to find out where the electrons are located. So I'm just going to put a line right here, because everything up until Rutherford's work, so this is where I'm going to divide. This is called early atomic theory. Past Rutherford's, so Niels Bohr's work and Schrodinger's work, this is called modern atomic theory. Okay, so in modern atomic theory specifically is where we understand where are the electrons in an atom. Because up until Rutherford's work, we didn't give location to the electrons. We know that they're around the nucleus, and that's about it. So understand, we're going to talk about them more in detail, but at least I want to introduce them. When it comes to the location of the electrons, the contributions of Niels Bohr, okay, is that he said these electrons actually are going to exist in circular areas, okay, which he called shells. At that point, he was saying like they are going to be like the rings around an orbit, because he was saying, oh, this is similar how the planets orbit around the sun. So he mentioned that these electrons actually live in different energy levels, what he called quantized energy levels. So he restricted the location of electrons. We're going to see later in this chapter how his model worked for particularly hydrogen, but then a new theory needed to be created. And in 1926, Schrödinger created equations to explain the locations of electrons, okay, past hydrogen. So he not only explained hydrogen, he explained every single element in the periodic table. Schrödinger's model is so good that even though it was created, as you can see, almost 100 years ago, it is what we currently use to understand the location of electrons in an atom. So this is my history lesson of how we actually know what an atom is. So to summarize it, right now we know that when it comes to an atom, atoms in an element are made out of 3 different subatomic particles. Protons, neutrons, and electrons. You can see that those protons, neutrons, and electrons have a symbol, they have a charge, they have a mass, and they have a location. And all of that is summarized in table 4.5. Table 4.5, you're going to use in exam 1. Okay? Now, you can also see in this table that the mass of the proton and the neutron is going to be higher than that of electrons. Also, their location is different than the electrons. While the protons and the neutrons are in the nucleus, electrons are outside of the nucleus. Okay? Now, how does all of this relate to the periodic table, which is one of the things that we are dealing with today? Well, all of this information about protons, neutrons, and electrons, it is all in the periodic table. So when we look at the periodic table, there's so much information. This is a table that is so rich in information that once you learn how to use it, it is actually very wonderful. Let's actually relate it to the subatomic particles in an atom. So whenever we deal with a periodic table, and again, the one that I provided to you guys on Canvas doesn't have names, but some of them do, like the one that I'm illustrated here, we can see the symbol for a particular element. We already learned that there are periods and there are groups, and we learned their names and the characteristics of the elements that are there. Now, when we relate the information of the periodic table to the subatomic particles, it is important to note that every element has an atomic number. It has been illustrated experimentally that that atomic number, which you can find on top of the symbol, is equal to the number of protons in a particular element. So far, we are talking about ground state elements. So our elements have their protons and their electrons intact. We are not dealing with ions until chapter 6. So understand that so far in our discussions, you're going to assume that your elements are at ground state. So the atomic number is also the number of electrons for elements, okay? So far, once we get into ions, is a different story. Now, understand that there's other pieces of information in the periodic table. And you can see here how specifically the mass number also gives us information about that subatomic particles that makes an atom. The atomic mass for an element, you must round it to a whole number. And once you have taken that value and rounded to a whole number, that is going to equal to the protons plus the neutrons in your element. So what does that mean? I already know that my atomic number tells me protons and electrons. When it comes to the neutrons, understand that you're going to take the atomic mass, which sometimes in textbooks are called mass number. Remember that you need to round it to a whole number, and you're going to subtract it from the atomic number. That's how we find the number of neutrons. Okay? So let's just do a quick exercise before I let you guys know, or before I let you guys go. Okay? So this is a table. It is actually more extensive in the in-class worksheet because there's other elements that have been incorporated, but let's do at least the first row. So you can see that in this table, you have the atomic number given, okay? Based on atomic number only, you can already fill in many of these columns, okay? So atomic number, which is the digit on top of the symbol, if it's number 4, what element are we talking about? What is the element? What is the symbol? Let's put it in the chat. Excellent. The symbol of this is Be, which this is beryllium. So when it comes to protons and electrons, remember, the atomic number is also the number of protons and electrons. Mass number, okay, I can obtain by adding neutrons and protons. So 4 plus 5 gives me a mass number of 9. Understand that in parentheses, I'm actually putting the value that is here in the periodic table, which for beryllium, if I leave it at 2 decimal places, it's 9.01. And the unit is AMU, because AMU is a unit of atomic mass unit. Any questions on how I fill in the information for the first problem in this table? Excellent. Since there are no questions, we are going to finish all the concepts of chapter 4 in the beginning of tomorrow's class. And then the last thing we're going to do is do the Kahoot quiz to review the material for the exam. I hope that you guys have an excellent day. Thank you for coming.